Okay, welcome back everybody. So for this lecture we're going to start on Chapter 5. Chapter 5 deals with chemical reactions and does one more transformation that takes us, instead of looking at constant temperature, volume, and number of particles, Chapter 5 is all about looking at the next transformation and allowing the volume to fluctuate and fixing the pressure instead. And if you might remember, the conjugate force associated with N is the chemical potential, mu. And you might wonder, well, why don't we flip that one as well? As we'll see, that's not actually possible, and you'll see why later. But really, chemical reactions and so forth deal with constant temperature, pressure, and number of particles, because that's sort of the realm in which reactions happen. They happen in a room, in a lab that has some fixed thermostat, and it's atmospheric pressure. So remember, when we go from V to P, we again have to do a Legendre transform. And the book kind of deals with these Legendre transforms in a different way. It doesn't talk about Legendre transforms and so on. But I like to talk about it that way. But let's do a little bit what the book says. So let's just go back and talk about free energies in general. Remember, early on we started with U, the internal energy, and it's a natural function of S, V, and N. What does it mean? It means that at fixed S, V, and N, right? At fixed S, V, and N, du is 0, and it's at a minimum. U approaches a minimum, right? We talked about this, and we can equivalently do this in terms of S, and then we have the second law, that S, naturally a function of U, V, and N, and if you hold the total energy fixed, the volume, and the number of particles, then the second law tells you that S increases and increases until at equilibrium it achieves a maximum. And so ds is equal to 0 at fixed, fixed U, V, and N, and S approaches a maximum. So what if you didn't have this? What if you were not at fixed U, V, and N, or S, V, and N? What if you fixed S, P, and N instead? Well, then remember we looked at the enthalpy, which was the Legendre transform of U, and the way that P was related to the derivatives of U in particular. Remember we had the thermodynamic identity, and because of that there was, let's see, so I can write it for you here. It was du is equal to T ds minus P dV plus mu dN. So this sort of recapitulates this statement, right? If you fix S, V, and N, these are 0, and then du is 0. And these are related to the partial derivatives of U. So minus P is related to partial derivative of U with respect to V. And remember, that's in the Legendre transform, that's what we had to subtract off, is the derivative times the conjugate variable. But here it's minus P, so we had a nice way to write the enthalpy as minus the derivative part, which would have been minus P times V. So it's what we, it's what we know. It's U plus PV. The book deals with it a little bit differently. It says, well, suppose you are at sort of fixed S, P, and N. well then what would H represent? If you're at fixed P, then H represents sort of the total amount of energy it takes to create your system at fixed pressure, right? It would be the internal energy plus plus here the work it takes to displace a volume V to sort of put your system inside a volume V. So this is kind of essentially a combination of the energy it takes for the internal pieces of the system plus the work associated with displacing a volume, V. So, and that was the enthalpy. Okay. So then, when we dealt with the canonical ensemble and we let the energy fluctuate, and we kept things at constant temperature, we looked at fixed T, V, and N. Then we had the Helmholtz free energy, which, unsurprisingly, it's an exchange of the dependencies of S and T. So instead of U depending on S, V, and N, we have a different function that now depends on T, V, and N. And that was just the Legendre transform again. U minus what? The derivative part, which is T, times the conjugate variable, S. So that's what it was. And so what does this represent? This you can sort of think about as the energy it takes to make the system minus the amount of heat you would get from the environment, right, that you would get if you're at constant temperature. If you're at constant temperature, remember that Q is equal to T delta S. So this is sort of U minus the amount of heat you would get from the environment if you were to create the system sort of from scratch. So then, you would create from zero entropy, from nothing, to all the way up to S. That would be your, so this is what it would be. This is the amount of heat you would get if you were to create the system from scratch. And so the book spends some time thinking about what these free energy what these free energies mean in terms of creating systems from scratch. So this is the heat that you would get when you create the system from scratch, from nothing. Okay. So what else? So alternatively, if you destroy a system, F would represent the amount of energy you could get out as work. Remember, so from here, what would you have? You would have U is equal to Q plus W. And if I solve this for W, what would I get? I would get U minus Q, right? And that's essentially U minus TS if this Q is referring to the system being made from scratch. So that would be like if you take the system and you destroy it, you reduce it down to nothing. That would get you some heat Q, and this would be the internal energy, and this would be the amount of work that you could get out of such a destruction of the system. So that's kind of the way the system, the way the book talks about these free energies. You can read more about it. I prefer to think of it really in terms of these ensembles. What are the experimental conditions? Are we fixing the energy, the volume, and the number of particles? In that case, it is the entropy that goes towards the maximum. Alternatively, if we fix the temperature, the volume, and the number, then in that case, it would be the free energy, the Helmholtz free energy, right? That goes to a minimum. We saw that. If we fixed S, P, and N, then it would be dH that goes to 0, and H would approach a minimum. So you see the second law has different formulations depending on what sort of control knobs you're using. This is natural U, V, and N because that sort of describes an isolated system, right? If you open up the system a little bit, let energy come in and out and fix the temperature, then it's no longer just the entropy that goes towards a maximum. Now you need to worry about the energy, the internal energy as well, and it's this combination that goes towards a minimum at fixed T, V, and N. And then there's this other case where if you fix S, P, and N, H goes to a minimum. It's sort of an analog of the kind of backwards second law where if you fix S, V, and N, then U, the internal energy goes towards a minimum. These are all the same statements. All of these guys, this is just a statement of the second law in different ensembles for different fixed quantities. And the last ensemble we'll worry about is the one where you combine these two guys, where you fix the temperature, the pressure, and the number of particles. And so let's do that. What do you get? Well, it's easy. You get the Gibbs free energy. These things have names, so let's write the names. So that's the enthalpy. This is the Helmholtz. F is, the Helmholtz free energy. To me, they're conceptually sort of the same thing, again, because I like to view this as what are your control knobs? Set those up. Once you set those up, you know what potential to use. And you know which one of them goes to a minimum. So the only funny thing is the second law, which S goes to a maximum there. So maybe, if I were to re-derive all of thermo, I would probably go back and define S with a minus sign, and then, S would go to a minimum. That would be more convenient in some sense, because then they would really sort of tie all these things together. But anyway, so you have the Gibbs free energy. So what's that? That's just two Legendre transforms of U. You can do them simultaneously. You take U, subtract off TS. That flips the dependence on S between S and T, and then you add PV. Flips the P and V dependencies. So that's pretty nice. Alternatively, if you read the book, you can think about this as, the amount of available work. G is sort of the available work at constant T and P. If T and P is constant, this would be the work done by the sort of environment, right? Due to the volume changes, this would be the heat. And so everything that's left over would just be other work. So we'll see that. But to me, I prefer to think about this as just changing from a function that depends on S, V, and N to a new function that depends on what? On T, P, and N. And how do we do that? Just two Legendre transforms. You take U, you subtract off the partial derivatives of U with respect to S, the variable we're interested in switching out, at constant V and N, times S. Right? It's a constant V and N because we're transforming U, which is a function of, remember, S, V, and N. Right? And then you subtract off du, dv at constant S and N times V. And what is that? You can go back to your thermodynamic identity and see what those things are. And of course it's U minus TS plus PV. This is minus P right here, and 2 minus times cancel it. You know, it's two Legendre transforms. I think it's a much nicer way to think about it. So what do we know? We can think about changes in free energies and the Gibbs and the Helmholtz. So let's try at constant T, we can try the change in F. And what's F? It's U minus TS. If T is constant, then it's delta U minus T delta S. First law tells us delta U is Q plus W minus T delta S. And notice that this delta S is always going to be at least, delta S is going to be at least as big as Q over T, right? It's equal to Q over T for a quasi-static process that's always close to equilibrium at all times. Otherwise, there's lots of ways you can have the entropy increase, so it's going to be bigger than this, typically. So this quantity here is always going to be less than or equal to the amount of work done. So that's just a true statement. The amount of work done is always going to, the change in free energy, if Helmholtz free energy at constant T for some process is always going to be less than or equal to the amount of work. If for a quasi-static process you'd have these equal, then it would be equal to the work. So that makes sense. What if we have a process that is at constant T and P? Here we didn't say anything about P, so just a true statement from the first and second laws. Constant T and P, let's look at what happens to delta G. Well, we go over here, constant T, constant P. What's that? Same sort of thing. Delta U, it's minus T delta S and plus P delta V. All right. Again, we use the first law. Plug in for delta U. What do we get? We get Q plus W minus T delta S plus P delta V. W is the work done on the system. We can say something about that as well. We could say, what's the work? Well, it must be the work due to volume changes at constant pressure, plus whatever other work you do on the system. So let's just rewrite this, Q minus T delta S. Have that over here, and W is going to be work other kind of work. Electrical work, something that doesn't have to do with volume changes, minus P delta V. That's the work done on the system, remember? And this gets canceled, right, by this term. So that's nice. Why is that? Because now you see T delta S is going to be bigger than Q, or at least as big as that. So now we see that at constant T and P, delta G gives you a bound for the amount of work you can get out. That doesn't have to do with volume change. And this is typically what you want for a reaction, because the volume in a reaction can change and all that, and you want to know the amount of work you can get out that's, not related to just simple volume changes. And that's what the Gibbs free energy affords you. At constant T and P, delta G for a quasi-static process where these are equal gives you the amount of work that you can get out from the system. So, it also tells you something else, right? It means that at constant T and P, if delta G, so let's look at this case, constant T and P, right? What does it mean? It means that if we were to find that for some process, delta G is positive, What does that mean? That means that to get the process to happen, you have to put work in. So for a quasi-static process, delta G is just equal to other work. So to get a process to go here, you need to put some work in. Positive work. Remember, positive W means you're putting stuff into the system. So if delta G is positive, then you need to put work in, and it would be a non-spontaneous process. Wouldn't happen just by itself. You need to put some work in to get your process to go. If delta G is negative, then this work would be negative, and you would get it out of the system, and this would be a spontaneous process. It would happen by itself, and you could use it to get some work out. Right? So that's nice. So already at constant T and P, the sign of delta G tells you whether or not a process is going to occur spontaneously or not. What else do we know? How about delta H? What does delta H say at constant T and P say? Well, let's look at delta H. Delta H is delta U plus P delta V. And from the first law, delta U is Q plus other work, same other work as here, minus the change in volume work plus P delta V. And you get that it's Q plus work other, because these two terms cancel. So if there's no other work done by the system, then delta H tells you something about the heat flow inside this process in a reaction. It's typically the process that we're dealing with, that we're calculating delta G's for, is some sort of reaction. So, so what do we know? From here, we can conclude something else, that if delta H is less than 0, and if really the dominant contribution to delta H is this heat flow, then what does it mean? It means this Q is negative, so that means heat is leaving the system as this happens. And so this would be an exothermic reaction, exothermic process. There's a flow of heat out, exothermic. If delta H is positive, then heat has to flow into the system, so it must absorb it from the environment somehow. And in that case, you would identify this as an endothermic process. So this is all these terms that you might have heard them from if you ever take a chemistry class. That's why they come up, is because in chemistry you're dealing with this constant T and P ensemble. And so all of a sudden these terms, spontaneous, non-spontaneous reaction, exothermic, endothermic, they come up. And where they come from considering these thermodynamic potentials and how they change over the course of a reaction. So now we should just look at a reaction and see what delta G and delta H are. Just do an example. So let's do an example. Let's do the hydrolysis of water. Hydrolysis is when you lyse water, you break apart water. You take water, H2O, and you do some work on it. In this case, you do it with electrical work, and you rip apart the water molecule into hydrogen and oxygen gas. So we're going to do that, hydrolysis. Hydro water, lysis to cutting water. So you take water, H2O, it's typically in the liquid state, all right, and you do some work on it and you convert it to hydrogen gas and oxygen gas. And you have to balance the H's and O's because, you know, the number of hydrogens over here is equal to the number of hydrogens over there. Remember, it's fixed T, P, and N. The fixed N is what tells you that the number of stuff over here has to balance the number of things over here. 1 O, so there's 1 O here. You can multiply both sides by 2 to sort of balance it out. But I want to calculate things per mole of water molecules. So that's why I have this half. So you can look up in a table for this reaction various things. You can look up delta H, say. And again, usually you're working at, you know, T is room temp, so, you know, like about 300 Kelvin, whatever it is, and P is about 1 ATM. That's what things are tabulated at, because most reactions you do at sort of ambient conditions of like this room. So you look it up what delta H is for this reaction at this temperature and this pressure. And it's 286 kilojoules. Again, these things, you know, for reactions are typically tabulated per mole of water that gets converted. And you can look up delta G, and that's 237 kilojoules. Okay, so what do we know? First of all, we know that delta G is positive, so you need to put work in to get this to work, right? You need to put work in. If you need to put work in, then in some sense this delta H doesn't really tell us anything much, because it'll be complicated. If we're putting work in, then that work other is non-zero, and that contributes to delta H, and we don't know about the balance between Q and work other, right? So it's, remember delta H here, where is it? It's Q plus work other, so since work other, we have to put things in. We can't connect it to a heat flow. Incidentally, if you reverse the arrow and you put minus signs on these, if you go the other direction, what would you get? You would get negative delta H and negative delta G. That would mean a spontaneous reaction, so you don't need to put any work in. And if you don't put any work in, this negative H would be the heats that you can get out of it. So it would be a spontaneous exothermic reaction. It means it would heat up. This would correspond to essentially the ignition of hydrogen gas, right? If you ignite it, spontaneous process, it will release heat, and you would get water vapor out. So, okay, but we're doing the other direction, so we need to put work in. And delta G actually just tells you the amount of work you need to put in. Why does it do that? Because delta G is delta U plus P delta V minus T delta S. And that is the electrical work we need to put in, because it is the work other, right? At constant P and T. Remember from before. right? Again, assuming that Q is equal to T delta S. Okay, so you can sort of have a picture of this. You can put your water or whatever it is in a box, okay, and calculate the change in internal energy of your system. And this delta G is the amount of work we put in. And what does it go towards? It goes towards changing the internal energy of the substance during this conversion process. And that'll be comprised of some change in volume. So the work you have to put in has to go into delta U, has to go into P delta V. In this case, what is it? It would be in the creation of enough volume for these gases. The liquid, when you go from a liquid to a gas, the gas occupies a lot more volume than the liquid. So most of this volume change has to do with the gas appearing and displacing a whole bunch of volume. So that's what that work goes. And then you get some heat from the environment. If delta S is negative, if it's positive, which in this case you would expect it to be because you go from a liquid, which is a low entropy state, to a gas, high entropy. So this would be positive. So you wouldn't need to put in that much work. You'd need to change the energy of the system. You would need to displace the volume, but you would get some heat coming in from the environment that would help you with that. So you don't need to put in as much as you think. And so you can draw this little, and this is the heat that comes in. And this is pushing the atmosphere away by the gases, by the creation of the gases. And this is the amount of electrical work you put in. So you can draw this little diagram that's kind of like an engine diagram of where all the energy flows come from. So let's figure it out. First of all, you could figure out what the P delta V is. P delta V, this is just as a sort of an aside, P delta V has to do with the gases. And if you think about it, PV is NKT, and we're at fixed T, so it really has to do with the production of, and since we're doing molar per mole, it's convenient to PV is equal to RT, or nRT. It's the number of moles of gas times RT. So the change in delta V is associated with the creation of the gas molecules, delta N. And how many moles do we make? We make 1 plus a half, right? So P delta V is really 3/2 RT. And I don't remember numbers very well, but I do remember that R is about 8. I do remember that, so it's about 8 joules per Kelvin. And I remember the units because I know that when I multiply by T, I better get out an energy, PV. So then this is multiplied by 300-ish Kelvin. That's the room temperature. So what is it? I get 8/2. It's 4 times 900 joules, which is about 3.6 kilojoules. So that's the P delta V contribution. But if you go and look at tables of, say, delta G's and so on, you get much bigger numbers than this. 4-ish kilojoules. You can look up tables of this. So this thing right here is delta H, right? And we know now it's comprised of delta U and P delta V. And you can look all these up. You can look up this guy, you can look up the change in enthalpy. And so if you do look at a table like that, you better make sure that it satisfies this equation, that delta G is in fact equal to delta H minus T delta S. And it is. You can look it up. Well, for this, it's 237. See, these are big numbers compared to the P delta V. It's usually P delta V doesn't matter. And the change in enthalpy tells you about the change in U. So it all kind of works out. You can 237, delta H is 286 kilojoules, and you get minus, when we put in the real number here for room temperature, 298 Kelvins, usually the standard temperature. And delta S must be 0.163 kilojoules per Kelvin. Well, it all kind of balances, right? This is positive, that's good. So it all kind of makes sense. See, delta H is bigger than delta G, the amount of work you have to put in. And that's because, again, you get some, from the environment, you get a little bit of heat to help your reaction along. So it's not a spontaneous reaction. You have to put work in, but you don't have to put in as much as you'd think because you get some heat from the environment. And you know that right away just from these numbers, that delta H is bigger than delta G. So you see this delta H is big, so there must be some negative contribution from the T delta S. Okay, so that's sort of a little example of a reaction and all the different pieces that goes into it. Where this is also useful is you might wonder, how do people calculate battery voltages? There's a reaction going on in batteries as well to generate a voltage. So you might wonder, maybe we can use these considerations to calculate how many volts a battery produces. So we can do that. How does a battery work? Well, a battery has a negative and a positive electrode. So, I mean, it's usually, like a wet cell is if you think about some liquid, right? It's a big vat of liquid, and it's got these two metal bars. One is negatively charged. They stick inside this liquid, like that. Let me get maybe some other color. And you got some positive electrode like that, sitting in the water. And there's a reaction that happens in here. There's ions inside. So this is, some water, aqueous solution of ions, of charged particles in here. We don't know what they are, but typically there's some positive charges, and they get converted in this reaction to some other kind of positive charges typically. And then there's reactions going on inside these pieces of metal typically. The negative part is called the cathode. And this is the anode. This is negative. Remember, electrons are negatively charged, so and the electrons will gather here, and then you can run a current like this from negative to positive and have the electrons move to the positive part where they want to be. So some amount, NE, some n number of electrons in this reaction will go from this side to that side. And there will be some reactions in here. You'll have some initial state of the cathode, and it'll go to some final state. It's just some material. It'll go from some initial state to some final state, and in the process, it'll produce some ions. It'll produce this I1 ion. That's how they get into this solution. It's positive, and it'll produce N electrons, like that. These ions will float around in here, get converted to I2 ions. These N electrons will move through the current, through the circuit that your battery is attached to this side. And over here, what happens? Your anode goes from some initial state. It receives the I2 ions. So in here, the I1s that come from here get converted to I2s, some other kind of ion. That gets eaten up by the anode, along with the electrons that come in from the circuit, leading to some final state AF. And this is the reaction. Goes around like that. So there's a total reaction. What's the total reaction? The total reaction is, you see these ions are kind of mediators. They just travel around here. The electrons in these ions just travel around. And really, what happens is the total reaction essentially is that the cathode and anode go from some initial states to some final states. And the battery gets eaten up over time and used up. And usually the ions aren't really part of the net reaction. They can be sometimes. But let's break this up into the kind of component reactions, right? Here and here, sort of 1 and 2. 1 and 2. In 1, the cathode goes to the final state and produces some ions. And here, the anode eats up the ions. And goes to the final state. And so we see for each mole of C, we get N moles of electrons moving around. So you can then calculate the amount of work you would get from that. Per electron, right? The amount of work you can get per electron must be minus delta G, right? That's the amount of work we can get out. That's why the minus sign. Divided by the number of electrons that go around. Well, there's N that go around. N. And how many is that in a mole? Well, it's N times 6.02 times 10 to the 23. That's Avogadro's number. And the units here must be joules. That's the amount of work we can get per electron. And what does it mean? It means we can use this formula to calculate the voltage that you can produce with the battery. Why is that? Because a voltage, remember that another unit of joules of energy is electron volts, and that's the energy associated with accelerating an electron across a particular voltage. And if this is the amount of work we can get per electron, it must also be the voltage across which we can accelerate the electron. So for instance, a lead acid battery, you can look up what delta G is. Delta G is minus 393 kilojoules for the total reaction. And N, the number of electrons that go around the reaction, there's 2. So the work done per electron is 393 kilojoules divided by 2 times 6.0, 2 times 10 to the 23 kilojoules, and that's about 2, you can calculate it, you can figure it out, 2.04 electron volts. So a lead acid battery does this amount of work per electron, and that corresponds to a voltage of what? 2.04. So the voltage of a lead acid battery, one of those cells, batteries have many of these cells typically, but one of those cells has a potential of 2.04 volts. Pretty good. So that's how you would calculate the voltage of a battery. If you're interested in the particular reaction there, for the lead, I can tell you what it is. It's the net reaction is you take the lead and there's this oxidized lead, there's the ions that move around. So this is the net reaction, and this is this part, the anode and the cathode part, and it's these guys. See, sometimes the ions are part of the net reaction, and the net reaction is just this, and you can calculate, you can look at a table and calculate delta G for this. And during this reaction, 2 electrons run around when you break it up into components, and see where there's an intermediate step where it produces 2 electrons which run around and then complete the reaction. This is the net reaction. Calculate delta G for it, and there you go. You can calculate the voltage of a battery. So that's pretty cool. And what we'll do next time is something a little bit more formal. We'll look at thermodynamic identities for G, and H and U. We'll remind ourselves about all that, and we'll talk about Maxwell relations, and we'll sort of try to put it all together so that it doesn't seem as intimidating when you flip between all these thermodynamic potentials. So that's for Friday.